Okay, Ed, we can see you coming down the ladder now.
Very great to be coming down.
Roger, bottom step.
The last one is a long one. Ascent check, very easy to do. Little push and just spring right up.
Well, on behalf of Fort Lewis and the Powerhouse Science Center, which we're very excited to partner with, we have an opportunity to talk about something that isn't COVID, that is actually space, and will stretch our brains. First up is Dr. Callie Cole. She received her PhD from CU Boulder, where she studied astrochemistry. If you're not sure what astrochemistry is, you're going to find out. Callie does instrumental analytic chemistry, but she's going to pursue two big questions. What do we know about molecules out in space? And what have we recently learned about them? So without further ado, let me turn it over to one of our great faculty at Fort Lewis, Callie Cole.
Thank you so much for your introduction, President Striticus. Like you just heard, my name is Callie. I teach chemistry up at Fort Lewis College, and I studied astrochemistry for 5 years at CU Boulder. Perhaps you've heard of astrochemistry before, perhaps you haven't. The one sentence that will form sort of the foundation of my discussion of astrochemistry today is that over 200 molecules have been detected in interstellar space. So today I'd like to discuss two key questions. The first, how did we detect those interstellar molecules? And the second, what have we detected so far? So how do we detect molecules that are not on our planet? We do not fly out to interstellar space with a vial and collect molecules and bring it back. Rather, we use something called spectroscopy, which involves detecting the light coming from molecules or the light that is missing that molecules have absorbed out in space. Not so long ago, we thought interstellar space was empty. In the year 1937, using a telescope at Mount Wilson Observatory, CH radical was detected. Shortly thereafter, in the early 1940s, CN was detected, then CH plus, then OH, and eventually the first polyatomic molecule, ammonia, or NH3. Slowly, we detected these because we were looking at the absorption and emission of light from these molecules. In 2018, we've begun detecting a lot more complex molecules. And in January of 2018, benzonitrile was discovered. It's this big one in the middle. It's a ring molecule, which is very exciting. Ring molecules make up all of our genetic material, so we're very interested. And like I said at the beginning of this talk, over 200 molecules have now been detected. How though? Wavelengths outside of the visible were used to detect different molecules. So for example, the very first molecule to be detected, CH, back in the year 1937, we detected the absence of radiation because this diatomic molecule absorbed light from a background star. And so we were able to detect the absence of that light and inference that this molecule was absorbing. So molecules can both absorb and emit radiation, and we can detect that using telescopes. We've been able to use all sorts of different telescopes to detect the radiation. So the Hubble Space Telescope is one that we've used. Also, there's an array of telescopes in the Atacama Desert in Chile called the Atacama Large Millimeter Array, or ALMA. ALMA is really cool because we just detected a brand new molecule in the atmosphere of Saturn's moon Titan called cyclopropanilidine. The more organic molecules that we detect in extraterrestrial locations, the more exciting it is for our knowledge of the origin of life. And Titan is known as an early Earth analog. It has an atmosphere that is predominantly nitrogen. We're sort of watching Titan just to see what chemistry develops there to get an idea of what may have happened on early Earth before the rise of oxygen. So that's pretty exciting. The telescope I'm most excited about is the James Webb Space Telescope. It launches in 2021. It's going to be able to detect photons much better than the previous telescope we'd been using, which was Hubble. And so using these telescopes, we're able to detect light, and that light coming from interstellar space allows us to determine what molecules are present. So the second question that I articulated at the beginning was like, what molecules have we detected extraterrestrially? We've detected quite a few. since 1937, when CH radical was detected, over 200 molecules have now been detected. So the list in chronological order is shown here. I actually like ran out of space and then just put the ones that have been detected since 2019 at the bottom right there. You can see the complexity of the molecules has grown over time. We've now found charged species and neutral species. So just to show you a little bit about this list, 75% of these molecules contain carbon. Our genetic material is carbon-based. So the life as we know it on Earth is carbon-based. So we're pretty interested in carbon molecules. There's some everyday molecules that we've detected out in space too, like laughing gas, nitrous oxide. There's the components of salt and vinegar chips. These are all interstellar molecules. So out in between stars in space, we've detected sodium chloride and acetic acid. We've detected ethanol. Also, this is a little fun fact for you guys back home. We've detected most of the molecules that make up your stinky breath and farts and stinky feet. CH3SH, H2S, these are all interstellar molecules. If you smell your foot right now, chances are you're smelling some interstellar molecules. Oh yeah, another really cool molecule is the buckyball. We detected that out in space. It's got 60 carbon atoms and it looks kind of like a soccer ball. And so I just wanted to show you this slide that like is my best effort at summarizing the overall process of chemical processing out in space. And this slide was created by Dr. Alexander Thielen. There's a lot of complicated chemistry that happens out in space. If you start on the far left of this slide, you can see that molecules can build up from single atoms and ions into larger molecules. That's what I was mostly working on at CU Boulder. But on the right, you can also start with like carbon stars. They can act like sooting candles. I really like that analogy, where large carbon molecules are coming off like that fullerene molecule I just showed you. Those can then interact with UV radiation. They can collide with other things and become smaller and smaller. They can deposit on asteroids and comets. And then as a comet approaches a star, it develops this tail where a lot of the molecules burn off. They re-enter the gas phase and interact with one another. So it's just a big soup. There's a lot of molecules out there. They can react on surfaces and in the gas phase, and astrochemistry is really cool. So basically back in the early 1900s, we thought of space as completely empty. It was a vacuum. It was a void. Nowadays, we understand a lot more is going on out there than we previously understood because we looked at wavelengths of electromagnetic radiation outside of the visible.
Charlie is the NASA Colorado Space Grant Consortium affiliate director at Fort Lewis, which means he runs all the FLC observatories, which is just amazing, and does great hands-on work with our students. He received his PhD from Rice and joined Fort Lewis after he had spent some time at the Johnson Space Center. And both Callie and Dr. Higgs do a ton of work out in our middle schools and high schools, inspiring youth to get interested in science.
First of all, I wanted to congratulate everyone for choosing to live in Durango, which is one of the best places to do stargazing in the country. So the very first question I always ask a class when I'm teaching an astronomy class is about how many stars can you see in Durango? And this is if you go out of town where it's nice and dark and get your eyes adjusted to the dark and you don't have any street lights by you. There's only about 4,000 stars that you can see with your naked eye. The way you can find out how many stars you see is first just look for the dimmest star you can see. And once you know the dimmest star, then look at a table and find out how many stars that makes up. So these numbers are for both hemispheres. So this is the total in the sky. And since we can only see half of the sky at once, it's about half this number. So if you are in a city that has the dimmest star you can see is magnitude 4, then you can see roughly 250 stars in the night sky. Durango is somewhere better than magnitude 6. So the total number of stars in the sky is 8,000 or 9,000, and half of that would be about 4,000. So I'm talking about magnitudes, and it goes from -1 up to 10 here. Well, what magnitude is, historically, it's just a measure of how big the star looks in the sky. We've been using the same magnitude scale for roughly 2,000 years. Yeah, here's the key. Big numbers just mean dim stars. So the bigger the number, the dimmer the star. So we know that stars are all different magnitudes, all different brightnesses. And if you look carefully at a photograph, you can see that stars are all different colors too. And what the colors tell us is the temperature of the stars. That's really useful information. But if you are going to go shop for water faucets and you have a blue knob and a red knob, everyone would put the blue on the cold water and the red on the hot water because we're used to thinking of blue as cold and red as hot. Well, it turns out that's not the case for stars. And you might know that if you go, instead of shopping for faucets, go shop for light bulbs. And most light bulbs that you go try to buy, they will give you the effective color temperature. So you can see this 1000 Kelvin is what they call warm white, but even though warm white is much cooler than cool white, they have cool white is up at 4000 Kelvin. And you can see that the daylight white, the 6000 Kelvin is what we would just call white. That's like sunlight, which has equal amounts of red and green and blue and all of the colors in equal amounts. And so it looks white to our eyes. So all of the colors have some amount of all of the other colors. It's just what the ratio is, blue versus red. And if it's a cool star, it has more red compared to the blue. And if it's a hot star, it has more blue compared to the red. So I guess that means if you're going to visit an astronomer, be careful which way they configure their sinks. Okay, constellations, when people want to be able to find their way around the sky, they want to be able to identify constellations. And there's 88 constellations in the sphere, and many are historical. 88 that's both northern and southern hemisphere. So at any one time, we can see roughly half of that, or 44 constellations. One thing I wanted to mention today, it's a word that most people aren't familiar with, and that's an asterism. And an asterism is just a noticeable pattern of stars. And sometimes an asterism is a constellation. Sometimes it's just part of a constellation, and sometimes it's part of several constellations. Something that's up high in the sky right now is the Summer Triangle, which is actually part of 3 different constellations. So here's one that a lot of people recognize. There's the Belt of Orion, and is Betelgeuse and Rigel, the bright star, and then here's the Orion Nebula. You can see that with your naked eye. The stars in a constellation are all different distances. They're definitely not associated with each other. It's just they happen to be in the same direction. So in 3-dimensional space, some of them are much farther. And if they're farther, they just are that much more luminous. Now here's a good example of an asterism that people would recognize. This is the Big Dipper. And so there's the handle part of the Big Dipper and then the dipper part at the top. It is an asterism because it's only part of the much larger constellation Ursa Major. So Ursa Major is the Big Bear, and it goes way off the field of view here. So the nose is up way above the screen and the legs go down below, and then the handle of the Big Dipper is the tail of the bear. Okay, other things to see real quickly. There's a lot of things you can see. Comets, I don't know if you saw the comet this summer. There's also meteors. Just going outside later this month is the Leonid meteor shower. And there's the moon. The red one is the moon during an eclipse. This half moon at the bottom, interestingly, is just holding my iPhone up to a telescope and taking a picture through the eyepiece. So that's one of the things you can see. Or just go outside and look at the Milky Way. There's a lot of things you can see here that you can't see in other parts of the country. So here's the biggest question I get when someone finds out that I'm interested in astronomy and have telescopes and run telescopes. And that's, what kind of telescope should I buy? I want to get something for Christmas. And well, there's a lot of different kinds of telescopes out there. What I always suggest looks like this. If you don't have a pair of binoculars, I'd say go get a really good pair of binoculars, spend whatever you think you want to spend on a telescope and buy a good pair of binoculars, because generally it's only a couple $100s that people want to spend, and you can get a really good pair of binoculars for $200. But a telescope, it's going to be kind of an intro telescope that you'll end up giving away after a couple of years. Binoculars, there's all different kinds of shapes and sizes. Binoculars are identified by a couple of numbers on the back, and 10 by 50 that you see at the bottom here is a pretty common astronomical type of binocular. Sometimes you get 7 by 50. So what the two numbers mean, the first number is the magnification, and the second number is the diameter of the front lens in millimeters. So 50 millimeters is about 2 inches. So this 10 by 50 magnifies a factor of 10 and has a front lens that is 50 millimeters across. The reason the size is important is because you want to compare it to your naked eye. Now, your pupil is roughly 1 millimeter diameter. And so this 50 millimeter aperture is going to have about 50 times more light gathering ability than your naked eye. So you'll see stars that are 50 times dimmer just using this pair of binoculars. So with binoculars that you're going to look at the sky with, bigger is better. So this 16 by 80 can see a lot more light than even this 10 by 50. The problem is they get big and heavy. Anything that has greater than 50 millimeter diameter, it's hard to hold just because it's heavy, and your arms will get really tired if you're holding it up looking at the sky. So I've seen fairly cheap binoculars, but I would encourage you to spend as much as you can, but all of these things are important for stargazing. Next thing is telescopes. These are just bigger binoculars. Actually, the optics in telescopes is simpler than most binoculars. And when I was learning about telescopes a long time ago, I know there were two types. There's refractors and reflectors. Reflectors have mirrors, and that's like what we have over on the right. These just big cardboard tubes that have a mirror in the back. And then refractors have a lens that will bend or refract the light. And that's kind of what a magnifying glass will do. It will bend the light into a focus, and you take another magnifying glass and look at where the light is focused. I can scroll through and see some of the cool pictures we've taken, putting a camera out on a tripod and leaving the lens open. And these are all just pictures that were taken at the observatory here.
Ignition sequence start. 5, 4, 3, 2, 1, 0. Launch commit. Liftoff. We have liftoff with Apollo 14. 3 minutes past the hour. The tower is clear.
Houston is controlling. Good route now. 16 seconds. Pitch and roll program started. 14 maneuvering to a proper flight course.